Okay, let's continue with our ENCOR infrastructure lab. In this case, we're going to go and configure NAT overload. Remember that NAT overload is a combination of NAT and PAT. But before doing so, we need to fix two things first. We have to do route leaking and route distribution. We're going to have to do route leaking because remember that we have this VRF internet that we created here that is attached to gigabit 60. And this VRF internet is the only VRF so far that knows about the default route that will help us reach the internet. Remember that we are using BGP in order to land this particular default route within the internet VRF. So far so good, but we have other VRFs that are our production VRFs. Remember that we, for instance, we have the VRF users in the blue network and in the green network. So this VRF user exists here, 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 and here. And we also have the VRF guest that exists in the blue network and the green network. So for instance, the VRF guest also exists here, 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 and here. These two VRFs do not have the default route. So we need to perform route leaking from the internet VRF into these two VRFs. So these users VRF and guest VRF will be able to know the default route. So the first action will be doing that route leaking, and then the second action will be actually redistributing these default routes. Now that the VRFs users and guests know about this route, we are going to use OSPF version 3 in the blue network. So we are going to redistribute this default route for both VRFs for downstream devices. So by doing so, switch 3 will now the default route within the VRF users, and will know now that the default route exists within the VRF guests. The same for switch 4, and using GIGRP on the green network, we're going to do the same. So the Nexus 3 device and the Nexus 4 device will have the full route within the VRF users and VRF guests. And after doing that, those two shores, we are now be able to now create a NAT threshold here on router A1, router A2, router B1, and router B2. So this will be my inside interfaces. This will be my inside interfaces for NAT. And these interfaces here, gigabit 60 at each router, will be my outside interfaces to perform NAT. So we are going to perform NAT. So to change or to NAT the IP address that exists here, that begins with 10, and we are going to change that for this set of IP address that begin with 189 that simulate the internet within this lab. We are going to perform another NAT here because we need to change this IP address that start with 189 into another set of IP addresses so we can reach the internet. So in this case, this will be my inside, and this will be my outside. So we're going to perform something that is known as NAT 44 because we are NATing twice the IP addresses. So we're going to perform NAT overload here, 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 and here. Let's go for the lab. So let's go for router A1 first. Notice that, remember how we configured the internet VRF. Remember that we configured this particular route export for the internet VRF. If we go and examine how the prefixes that live within the BGP RIP for the VRF internet, we will see that these prefixes use this tag, this particular route target. So if we issue show IP route VRF internet, we will see that we have a default route living there. But if we issue show IP route VRF users, we don't have a default route. And if we issue show IP route VRF guest, we see that we don't have the full route either. So we are going to use this configuration within the VRFs in order to import the routes that live within the BGP RIP for the VRF internet into our VRF. So we are going to use this particular value, 65,000:1000, as an import for my other VRFs. That will be the trick, the hack, in order to do route leaking. So let's do that. So let's configure now the VRF users in the address family IPv4, and I'm going to do route target, but now import with the value 65,000:1000. And I'm going to do that as well with the VRF guest address family and import. So that is the hack, that is the trick. That is how we are doing route leaking. Now, if we issue show IP route VRF users, I should see the default route. It takes a while. Now we can, while that happens, we can see how our VRF definition ends up. So show run section VRF definition users. So now we can see that we added this line. So this is the line that is doing the trick. So if we issue show IP route the VRF users, we see a default route now. And if we issue show IP route VRF guest, we can see this route actually comes from the VRF internet. So we are going to do the same with router A2, router V1, and router V2. Okay. Let's go to router A2 and configure the same, just importing the route target that belongs to the VRF internet within other VRFs, in this case users and guests. So that will be our first thing to do. If we go to switch 3 and we issue show IP route VRF guest, we see that we still don't have the default route. So for instance, users, we don't have default routes yet. So now the second thing that we have to do is redistributing this default route through internal routing protocol. In this case, for router A1 and router A2, we're using OSPF. So let's go to router, to the OSPF version 3 router configuration, and let's go for address family IPv4 unicast VRF users autonomous. I think that's it. And then this is the command that actually generates the full route originate. We are going to leave it at that. I can issue the parameter always to always generate the full route within the OSPF domain, but I don't want to do that. I want to actually let OSPF know when I lose the full route from BGP. So this is what works. Now this will be the command. Now switch 3 should let's do that for the other VRF as well. So let's go for guest. So let's do the same. And now if we go for switch 3, we will see that if we issue show IP route VRF users, we should see the default route. So now the downstream devices have a default route for the users VRF and for the guest VRF. So let's do that here in router A2, router OSPF version 3.1, address family IPv4 unicast VRF users, and let's issue default information originate, but we are going to use a metric here. So the default route that comes from router A1 will be preferred over this one, because router A2 is kind of my backup router. So far so good. The route still exists here without changes. If we lose the default route coming from router A1, router A2 will take over. Now let's go and do the same or something particular similar for EIGRP. For EIGRP, we have to go through another route. Let's see, for instance, in Nexus, I don't have the default route for the VRF guest and user. So let's inject the default route that now it should exist in VRF users through the routing protocol. So let's go for the routing protocol. In this case, we have router EIGRP headquarters. Let's go for address family IPv4 unicast VRF users autonomous system 1, and then we're going to go for topology base. This particular command, topology base, is a command that only exists on named EIGRP. If you're using numbered EIGRP, you don't have to type this in. So this is a new configuration mode for named EIGRP, and we are going to redistribute the prefixes that come from BGP. This is our autonomous system number, and we're going to assign a metric here, for instance 1000, delay maybe 10, reliability 255, loading 1, and then 1500. So we should see now. Let's do that for the other address family. In this case, let's do that also for the guest topology base, and the same. Okay, now we should see something here in Nexus. So now we know the default route for the VRF users, and we know now the default route for the VRF guests. We are going to have to do the same for router V2, but we are going to modify the metric, so the router V1 metric is preferred, because router V2 is my backup link. So let's go for router EIGRP headquarters, address family IPv4 unicast VRF users, autonomous system number 1, topology base, and then we're going to do a redistribute from BGP 65 to, and then let's use this matrix 1000, and then 10. I'm going to change the delay here to 1000 to make it less preferable as router V1 route 255, 1, and 1500. Okay. Metric. Okay, that is what the action number 2 was all about. We have default routes here. Now let's go and do the NATing. Remember that at Internet 2, let's see, we are going to configure here. We are going to do the NAT here for the addresses 189. So at Internet 2, let's create first my access list. Access list 1 permit everything that starts with 899 will have permission to get NATed into the internet. So let's go for interface gigabit 2. This will be my outside, and my gigabit 5 will be my inside. Now let's issue the command IPNAT inside source list 1, interface gigabit 2 overload. This is the magic that does the overloading on only one interface. If I issue show IP NAT translations, I don't see anything so far. Let's see what happens if I ping the internet from the VRF internet here. I can ping the internet because this router is translating my IP address here. This will be my inside local 199.1.11.1, and it is translating into this particular IP address that is the IP address that we have on the interface gigabit 2. And that happens because I use the command overload. So this IP address is this IP address. This is the NATed IP address, and this is the NATed IP address. Notice that we are using overload because we are going to have a control of ports assigned to it. Now let's do the NATing on the other devices. Notice that we have several sub-interfaces here that we have to design as inside. So let me move this to see the interfaces. So we are going to configure gigabit 3.0 with this particular subinterface that belongs to the user's VRF and as inside, and then this particular subinterface that belongs to the VRF subinterface as inside. And then we're going to do the same with gigabit 4.0 and we're going to use these numbers 14.01 and 14.02 as inside, and gigabit 6.0, which is the link that connects me to the internet. This particular interface will be my NAT outside. So now that I have that, I can issue, I have to create an access list, permit, everything that begins with 10 will have permission to get NATed. So I will issue IPNAT inside source list 1 interface. I think that interface gigabit 6.0, and this will happen for the VRF users, and we are going to overload. We are going to do the same for the VRF guests. So we are going to perform two NATs here, one for the user's VRF and another for the one for the user's VRF and another for the guest VRF. So now we can issue show IP NAT translations, both for the VRF users and for the VRF guest. So let's go for one of our end devices here. Let's see what happens for a device that exists within the VRF users. Let me stop it. It is kind of blocked. And what we're going to do from this device, this particular device lives in a VLAN that is actually lives in the VRF user. So let's see if I can reach my default gateway. Okay. Let's see if I can ping the internet. I can ping the internet, and if we issue show IPNAT VRF users, I can see these pings being NATed from this IP address that belongs to this PC, which that has this IP address. is NATed into 189 whatever, and then this other router here is not in this other IP address into this other set of into this IP address that actually has access to the internet. So this is how it works. It already works. So we could go for a PC that is connected to the VRF guest. So let's see, for the instance, this one. Okay, this lives in this VLAN that belongs to the guest VRF. So let's see if we can ping the default gateway first. And then we'll have to ping the internet. Okay, we'll have to troubleshoot this. Let's trace route to see 10.24. Let's see who has that. 10.2.24.2. This should be this router A2. Okay, we are reaching this router, and then we should be able to ping through the internet. I have not configured NAT translation here, so we have to do that because this traffic is reaching this router A2. So we have to configure translation there. So let's configure NAT overload at router A2. Let's move this a little bit. So let's issue interface gigabit 30 subinterface 2301 IP NAT inside. And then for the other subinterface that belong to the guest VRF, we're going to do that. And then for interface gigabit 40 subinterface 2401, this one belongs to the user's VRF. And then let's go for gigabit 60, that will be my outside. And then we're going to do my access list. Access list 1, permit everything that starts with 10 will be allowed to get NATed, or in this case, NATed and patted. So IP NAT inside source list 1 interface gigabit 60 VRF users overload. The same for the guest. Okay, I have now NAT configured for these devices. Let's go back to the PC and ping. Now we can ping it. So this is the NAT translation. It is going through router A2. Okay. Let's configure that here as well. Router B1 has gigabit 30 and gigabit 40. So for gigabit 30 for the subinterfaces 1301 and 1302. This is the subinterface for the connection for the VRF users, IP NAT inside. Now the subinterface for the guest VRF will be this. Remember that we are using path virtualization, so we have some. That is why we have so many subinterfaces. and for gigabit 40 will be 1401 and 1402. So let's go for gigabit 40, 1401. This will be NAT inside, IP NAT inside, and for gigabit 60, that will be my NAT outside, and then my access list one that will permit everything that starts with 10 will be allowed to be NATed and patted. Now IP NAT inside source list 1 interface gigabit 60 VRF users overload, and the same for the VRF guest. So if we go now for this particular PC that belongs to the VRF users, has this IP address. Let's see if we can reach our default gateway. Okay, now let's ping the internet. Okay, we are pinging the internet, and let's see the NAT translation. Show IP NAT translations, VRF users. Notice that these resources are kept there for some time. Every time a user is being NATed with the overload option, some resources are assigned to this user, and these resources are there for some time. So remember that if you're running, you might run out of resources with the NAT overload using one interface. If you run out of resources using NAT overload using one interface, you can go and choose the pool option. You can also overload a pool of IP addresses, and you will need to go into that option if you are actually NATing too many users using a single interface. So let's go for the last part of the configuration. Let's do that. Router B2, gigabit 30, and gigabit 40. So in interface gigabit 30 subinterface 2301, that is a subinterface that belongs to the VRF users, IP NAT inside. Now a subinterface that belongs to the VRF guest, IP NAT inside. Then for gigabit 40 subinterface 2401, IP NAT inside. We have to do all of these because we are using data path virtualization, each path for each VRF. So that is why we have so many subinterfaces. And now my outside interface is gigabit 60, IP NAT outside. Now let's create an access list. Access list 1 permits everything that starts with 10 will be allowed to be NATed or unpatted. Then IP NAT inside source list 1 interface gigabit 60 VRF users overload, and the same for the guest. Okay, now let's see what happens with this this particular PC that is connected to the VRF guest. Okay, it has this IP address. Let's see my default gateway. Okay, and let's see if I can reach the internet. I can ping the internet. Great. We could see the NAT translations at router V2, show IP NAT translations, VRF guest. This is a guest. IP NAT translations, VRF guest. Oh, it went to router V1. That is funny. Probably we need to fix something in there. Okay. What happens if I do a trace route? I can see, for instance, this is my default gateway. This is most certainly router B1. This is the router internet 1. This is router internet 2. This is my internet switch that I have at home. And then we are going through the ISP here to reach this IP address. So that will be the path. Let's do that in another PC, for instance here. Trace. So this is the default gateway. This should be switch 3. Then this should be router A1. This is the router internet 1. And this surely is probably router internet 2. This is my switch or my router that I have that belongs to my ISP in my home, and we are going through the internet then in order to reach this. These hubs belong to my ISP. So let's see if we have some other commands. For instance, show IP NAT statistics. For instance, we have active translations, outside interfaces, inside interfaces, hits, miss, self-translated packets, self-pointed packets. Pointed packets are the packets that arrive into the router and Ceph is not going to process them. It is going to send them to the central CPU for processing. Expired translations. And that's it.